Okay, thanks. So I'm going to talk about optimal mechanisms for budget-constrained buyers, and this is joint work with Nikhil, Devanur. So let me just jump right into a problem. Hopefully, part of this seems very familiar to most of you. So say that there's a single buyer and a single item for sale, and we'll start with where the value is drawn from a distribution that's known to me, and there's also a public budget. So I know how much Nikhil is willing to, the maximum amount that he's able to pay, and so does he. Right, and so now what I'm going to do, I'm going to propose some menu, which is just a list of probabilities and how much each one costs. And Nikhil is going to arrive, and he's going to select whichever option maximizes his utility. And to be clear, his utility is his value times the probability he gets it minus the price he pays, but he can't pay more than his budget. And my goal is to maximize my expected revenue. So we know from actually early work that if this distribution happens to satisfy these technical conditions called regular or decreasing marginal revenues, then the optimal mechanism is deterministic and is actually not much harder than the case without a budget. So the optimal thing to do is just set a price that is either the minimum of, that is the minimum of what you would set if there was no budget constraint and the budget. Okay, so this case is easy. And actually it was later shown that if the distribution is irregular, then what's interesting is you might need to use randomization, but you don't need to use a lot of randomization. Okay, so 2 menu options suffice. So let me just give you an example. So let's say that Nikhil's value is drawn uniformly from the set 2 and 20, so 50-50 between 2 and 20, and his public budget is 11. Okay, now it should be clear the best single price that you can set here is 11. And whenever his value is 20, he'll choose to buy it. You get revenue 5.5. But there's something a little bit more clever you can do, which is you keep the price of 11 for getting the item, and you also offer this super cheap option to get the item with probability half and pay 1. And the idea is that the high value bidder is not going to deviate from paying you 11, but the low value bidder is now paying you something. Okay, and it turns out this is actually optimal for this example. Okay, so now let's go to the setting where the bidder's value and budget are both private, so they're drawn from some correlated distribution. Notationally, it's going to be easier to think of having the budget drawn first and then the value drawn conditional on the budget. Okay, and for this talk, there's only going to be finitely many possible budgets. Okay, and so again, the model sounds the same, so I can offer a list of options. This list is just a probability and a price, and the other thing I'm allowed to do, I'm allowed to add for every option that you need to prove to me that your budget is at least so large before I will let you purchase this item. So this is just a way for the seller to do additional price discrimination. And after this, it's the same as before. So I will post this menu. Nikhil is going to sample his value and his budget, and he's going to arrive. He's going to select whatever maximizes his utility of those such that he has enough money to prove that he's allowed to buy it. And my goal is still to maximize my expected revenue. Okay, so for this problem, there's again early work that shows that if each of these marginals happen to satisfy this decreasing marginal revenues condition, so this actually doesn't hold just when the distributions are regular, then the optimal mechanism is deterministic. And by that I mean that the menu just has for every budget a different price you can pay, such that if you can prove that your budget is at least so large, then you get to pay this price. Okay, and what maybe is just a little bit counterintuitive is that as your budget increases, the price you have to pay decreases, and the idea is just that you can always lie and pretend that your budget is less, but you can never lie and pretend that your budget is larger than it actually is. Okay, but following this, the open question is what if the distributions don't satisfy this DMR condition, and that's what we address in this paper. So we characterize the optimal mechanism for arbitrary correlated distributions over values and budgets. And I'm not going to actually give you a concrete statement of what the format is, but what I want you to take away is that it might require exponentially many different menu options, but that exponentially many always suffice. Okay? So one thing I would like you to think about this is how the heck do you possibly show that something that has 3 times 2 to the n minus 1 menu options is an optimal mechanism? And the answer is you use duality. It's very similar if you know this more recent paper with Yang and Nikhil. It's the same kind of approach. And what's especially nice about this is that it turns out that even though the optimal mechanism is a complete mess, the optimal dual turns out to be pretty simple. And it's actually not too hard to read off an optimal primal once you know what the dual is. The second thing I want to emphasize, it's a little bit different between this paper and other ones that use duality, is that we're able to prove complementary slackness without actually writing down a closed form for anything. So we're able to characterize that the optimal dual, I don't know exactly what it looks like, but it has some simple form. And then we can show that there's a primal that has some form and that they satisfy complementary slackness without actually any algebra in the end at all. Okay, so those are the things I want you to take away. And now, since I think the coolest things about this paper are maybe the technique, so I'm going to spend the rest of the talk just trying to give you some intuition about those. Okay, so the first thing we do is, actually like pretty much every talk I give now, is we write a linear program. And we take this partial dual by Lagrangifying the incentive and budget constraints. And this is going to look, again, very similar. If you've seen this work or follow-up to this, it's going to look very similar to this approach. And I will overview this. The second thing we need to do is once we have this dual problem, we need to try and find what does an optimal dual look like. And what I'm going to show you at the end is that there's basically these 4 basic operations that we can show always improve the dual. And that actually, once you can no longer do these operations, the dual cannot be that complicated. And this lets us characterize the optimal dual, again, without nailing down a closed form. I'm going to overview this part briefly at the end. OK, the third part that I'm just going to completely skip is once you have a dual, you need to show that there is a primal that complementary slackness with it. OK, in this part, if you're familiar with this FedEx problem paper from last year, showing that describing the primal is similar to this process, but if you're not, I'm just not going to say anything about it, and you can ask me offline. Okay, and again, the thing I want to emphasize about comparing to prior work is that often, when you show complementary slackness, what's nice about doing it directly is that it lets you, for instance, figure out exactly what the probabilities are, exactly what prices are, and sometimes you care about this, but often you just care about the existence of prices or some structural claim about the mechanism. And again, just to be clear, we're directly shooting for the structural result without going through closed forms as an intermediate step. Okay, so now let me write this LP for you. So again, I hope that most of this will look somewhat familiar. So we're just going to write for every possible budget and for every possible value that the bidder might have, we're going to say what is the probability that they wind up getting the item and what is the expected price that they pay. And then we need to make sure that whatever these variables are that describe the mechanism, that they actually correspond to a truthful menu and that they respect budget constraints, et cetera. So I'll ask you to trust me that actually the only deviations we need to worry about are ones where the bidder might try to keep their budget the same and increase their bid, or keep their value the same, keep their budget the same and increase their value, or keep their budget the same and decrease their value, or keep their value the same and decrease their budget. And remember, we don't have to worry about them lying by increasing their budget because they actually can't do that. They can't somehow prove that they have more money than they have. Okay, and we also need to make sure that the budget constraints are satisfied so that no one is ever asked to pay more than their budget, and also that these things that I'm claiming are probabilities actually lie in 0, 1. So the claim is that this LP actually completely characterizes what the optimal mechanism is. And subject to these constraints, we just want to find one that maximizes our revenue, which is, again, a linear function. Okay, so at this point, it's not clear that this LP is any easier to reason about than just a generic linear program. But a quick observation I want to make is that it's very easy to solve if we didn't have the truthfulness or budget constraints. Right? So if the only constraints we had are on the allocation probabilities, then it's very easy to reason about this. And what we should do is just observe that the price variables are unconstrained. And there's a positive multiplier here. We should just set one of them to plus infinity, and now we've solved the LP. The further observation I want to make is that actually this is still a very easy LP to solve, even if there's an arbitrary objective function, right? And so that's because for whatever multipliers show up in front of the price variables, If it's positive, then we know we should set it to plus infinity because it's unconstrained. If it's negative, we should set it to minus infinity. And same thing, these allocation probabilities, the constraints on them are independent. They don't interact at all. So if we have a positive constraint on the allocation probability, we should just set that probability to 1. And if it's negative, we should set it to 0. Okay, so the point is this is a very easy LP to reason about. And the annoying thing, so the point is that these truthfulness constraints and the budget constraints, they're annoying when they're inside the LP, but they're actually not that hard to reason about when they're in the objective. So we should move them to the objective with Lagrangian multipliers. And this is, again, following exactly the same approach as the work with Yang and Nikhil. It's just observing that every set of non-zero Lagrangian multipliers implies an upper bound on how good the revenue can be. Okay, so now I just want to, just to be a little bit clear, I'll write this for you. So the only constraints that remain in the Lagrangified LP are the ones that constrain the probabilities to lie in 0, 1. And then this is what the new objective looks like. Okay, so I've color-coded it, but you don't need to stress about this too much. Just observe that all I've done is I've taken the constraints and I've put a Lagrangian multiplier on them and moved them to the objective. Okay, and what I'd like you to first remember is that we observed before that if any of the multipliers for the price variables are non-zero, then you can get value infinity for this LP, so it's not a useful upper bound. And so what this means is that any interesting dual or any optimal dual that we would possibly want to study should have all of these multipliers equal to 0. Okay, and so on the next slide, I just want to give you kind of a picture as to what these constraints look like. So what I'd like you to have in mind is draw kind of this grid for every possible budget and value pair that the bidder might have. So as we go up, the budget's going up, and as we go to the right, the value is going up. And I just want you to imagine these two sinks in this source as additional nodes. Okay, so these are the nodes in the graph that I would like you to have in mind. And I'm just going to zoom in on one row of this graph. And I want to show you some edges that I would like you to imagine as being present based on the Lagrangian multipliers. Okay, so we had some constraints that said that you don't want to lie by underreporting your budget. And whatever multipliers you choose to put on those constraints, I want you to put them on edges going from the type that had the true value in budget and pointing towards the value in budget that they were thinking about reporting instead. Okay, so the red ones correspond to the constraints for underreporting your budget. We also had constraints that say you don't want to lie and underreport your value by a little bit or overreport your value by a little bit. And so again, whatever Lagrangian multipliers you choose to put on those constraints, put those values on these edges in your graph. And then whatever multiplier you choose to put on the budget constraint for budget I, put that multiplier on this edge going from this type to this budget sink. And then the last edges, so these values are fixed and don't depend on the Lagrangian multipliers you set. Okay, so for any multipliers you set, I would also like you to imagine there being an edge from this super source to every budget value pair, and the weight on that edge is equal to the probability that the bidder has this budget value pair. Okay, so the important thing to take away is not exactly what values go here, but that I want you to imagine this graph with weights on different edges depending on the Lagrangian multipliers you choose. And the lemma is that the partial Lagrangian is finite if and only if this picture conserves flow at all nodes. Okay, and the proof is really just a matter of observing that the multiplier for each price variable is 0 if and only if the flow in is equal to the flow out. Okay, so this is how you should think of potential Lagrangian multipliers. Okay, so going back to the partial Lagrangian, this is what we have so far. And now the next thing we want to remember is that we said, okay, so these are going to get zeroed out in any interesting dual. And now we said that if this multiplier is positive, we want to set this to 1. And if this multiplier is negative, we want to set it to 0. Okay, so that's pretty easy to reason about too. That means that whatever weights we happen to get, the value of the partial Lagrangian is going to be exactly summing over all budgets, summing over all values, the max of this weight in 0. Because that's what's going to result by setting this to 1 when it's positive and 0 when it's negative. So the new game is just trying to find a flow that minimizes this sum, and it has to conserve flow because otherwise the value is going to be infinite. Okay, so I have this at the top, but so if you're really sharp in real time, I'm going to show you 4 operations. It's possible to verify that they all decrease this expression using this at the top, which you can derive by flow conservation, but I'm not going to read through that. I just want to show you the 4 operations, and it should be obvious to you that they all conserve flow. And then that's going to be the end of what I'm going to share. Okay, so the first operation is just is exactly the same if you're familiar with ironing from Meyerson's auction, that if you ever have a situation where the weight associated with a lower value is positive and a weight associated with a higher value is negative, then you should add this cycle between them, and this will help balance them out, and it's easy to see that adding a cycle conserves flow. Okay, the second one we call boosting, and this one just says that if you ever have a case where the weight here is negative, and you were previously sending flow from here into here and all the way down this line, that what you can do that's better is instead of sending the flow down here, you can send it down and send it down to the left instead. Okay, there's this one that just says that if this value happens to be positive and you used to send flow down and left here, what's better is to send it left and down. And then this last one, I'm not going to describe in words, but if you stare at this picture, you can be convinced that these operations do conserve flow. And again, with a little more time, you could plug into this equation and verify that it's always guaranteed to decrease the dual. Okay? And so the claim is that once you can no longer do any of these operations, you can characterize that the dual must have some somewhat simple form. And subject to stuff that I'm intentionally hiding, this is enough to say that there is an optimal primal that's not completely ridiculous, that satisfies complementary slackness. Okay, so to wrap up, just to remind you, so I know I said this a couple times, that really what I think I would like you to take away is that even though the optimal primal is really messy, the optimal dual is pretty simple. And you can characterize the optimal dual with these basic operations. You don't need to get closed forms just to show that the optimal mechanism has certain structure. And we use that to find the optimal mechanism for a single buyer with a private budget with no assumptions on the distributions. Okay, this fits into kind of what's now an emerging direction in mechanism design. I forget who originally coined this term, but it's kind of like 1.5 dimensional mechanism design, in the sense that it's clearly more complex than single-dimensional mechanism design, but it's not completely bizarre like truly multi-item mechanism design. And actually, the next talk is on another topic that I would say is related to this, and there's a lot of other nice questions in this area. If I had to pick one, I think one barrier we haven't been able to break through yet is designing auctions for multiple 1.5 dimensional bidders. So that's everything. Thanks for listening.